All efforts have been made to ensure the information presented is accurate at the time of recording. Any references made to implied functions remains at the discretion of Broadcom and can change at any time. Welcome, my name is Andrew Firth from the VCF Technical Marketing team. Here, I'm going to show you through the new features and functionality that's been added into VMware Cloud Foundation 9. Let's take a look at what's new with vSphere 9 as part of VCF 9. The vSphere Lifecycle Manager of VCF 9 supports the configuration of mixed vendor clusters. For a mixed vendor cluster to work, the base ESX version is static and cannot be customized. However, the vendor add-ons, firmware, and components of each image definition can be customized to accommodate clusters with mixed hardware. Each cluster can be configured in this way with up to 4 additional image definitions, and each additional image definition can have a unique hardware support manager. Additional images can be manually assigned to a subset of hosts in a cluster or automatically using system BIOS information, including vendor model, OEM string, and family values. So what this means is that you can configure a single cluster, let's say with 5 Dell hosts and 5 hosts from HPE, where the Dell host can be assigned one image definition with Dell vendor add-ons and Dell HSM, and the HPE host can be assigned a different image definition with a HPE vendor add-on and HPE HSM. But all 10 servers in this example will be using the same base ESX version. vSphere 8 Update 3 launched with a tech preview for memory tiering. Now with vSphere 9, this feature is generally available. This capability allows you to use NVMe devices that you can add locally to an ESX host as a second tier of memory. Memory tiering over NVMe increases VM consolidation by directing VM memory allocations to either NVMe devices or faster DRAM in a host. This allows you to increase your memory footprint and workload capacity while reducing your TCO. It's well known that GPU capacity is expensive and in high demand. vSphere 9 and therefore VCF introduces several new features to make working with GPUs easier. Firstly, there is the ability to configure vGPU profiles. With this, admins can provide descriptive detail of a GPU type, how it's being configured. So for example, a GPU or a vGPU, time sliced versus MIG. Admins can quickly view what capacity they have available and the workloads assigned to each, which can help with capacity planning. vSphere 9 also introduces vMotion precopy, which is a technique used to transfer VM memory to another host with minimal downtime. It copies both cold and hot memory in multiple passes while the VM is still running. This eliminates the need to checkpoint and transfer all memory during downtime. And this can be particularly useful for AI workloads and can deliver a reduction of 3x in terms of vMotion time. GPU reservations are also new and allow admins to reserve resource pools for vGPU profiles ahead of time. A GPU reservation guarantees capacity for a new VM and can be used to assure that vGPU resources are available to power on a new VM. Live patch for ESX was introduced with vSphere 8 Update 3 and has now been extended to more of the ESX image, including VM kernel and NSX components, therefore increasing the frequency that patches can leverage live patch. NSX components, now part of the base ESX image, can be patched using the live patch process without hosts entering maintenance mode and without hosts needing VMs to evacuate the hosts. vSphere 9 also introduces a new hardware version. Hardware version 22 extends virtual CPU support for new VMs to 960 virtual CPUs and up to 24 terabytes of memory for a virtual machine. There's also a whole lot of new CPU models, including AMD Zen 5 and Intel Granite Rapids. There is extended guest OS support and an extensive new set of additional innovations, some of them listed here. vSAN now includes a number of new enhancements which we can now leverage within VCF. VCF 9 introduces deduplication for vSAN Express storage architecture. This is a cluster-wide deduplication technology that is designed for maximum levels of space efficiency with minimal impact on guest VM workloads. The intelligent design of ESA's deduplication technology will adaptively throttle the use of spare resources so that there is no compromise to guest VM performance. Furthermore, deduplication's integration throughout the storage stack means that the common vSAN data services such as compression, snapshots and clones, erasure coding, checksumming, and so on are fully compatible with deduplication. These new deduplication capabilities will help to further drive down TCO to levels not previously possible. New to vSAN storage clusters in VCF 9 is the ability to separate the back-end storage network traffic of the vSAN storage cluster from the front-end traffic used by the vSphere clusters mounting the data store. Separate traffic reduces the amount of communication to and from the vSphere clusters, and it keeps all of the east-west traffic from the vSAN storage cluster within its own network. Why is this important? Well, if the vSAN storage cluster resides in a single rack, this means that all vSAN storage cluster traffic can be serviced by high-performing switches, with no need to leave the top of rack. This capability allows admins to deploy and optimize a vSAN storage cluster with minimal investment, and makes it easier to adapt to running environments of older networking. vSAN in VCF 9 improves its native file services by increasing the maximum number of shares per cluster. Now, customers can create as many as 500 shares per cluster, which is up by 250 shares per cluster from the previous release, and 100 shares per cluster in prior versions. This enhancement is specifically targeted at customers who use NFS exports and satisfies a variety of use cases. Whether one chooses to use vSAN file services for departmental file shares, project collaboration, or sophisticated microservices architecture using persistent volumes, the increased scalability will help deliver these capabilities with room to grow. vSAN stretch clusters have proven to be a popular topology deployed by a large percentage of our customers. They are an easy and reliable way to achieve site-level resilience without some of the complexities associated with metro storage clusters using storage arrays. For VCF 9, vSAN introduces new features to further improve the flexibility, uptime, and operations of stretch clusters. First is the support of stretch compute clusters, mounting the data store of a stretch vSAN storage cluster, making stretch clustering for vSphere clusters even easier. Next, the new site-wide maintenance capability takes the concept of maintenance mode to the site level for a stretch cluster. And then there is the new stretch cluster manual site takeover capability, which gives the administrator a self-service approach to recovering a single site in the event of a severe double site failure of a stretch cluster. Let's now take a look at what's new with VCF Networking with NSX. Many of you may be familiar with virtual private clouds. A VPC is a logically isolated tenant-specific virtual network that provides dedicated routing, switching, and security services. In VCF 9, VPCs are implemented consistently across the entire platform, not just within NSX. This model defines clear roles to support multi-tenancy and enables self-service capabilities for end users. The first role in this model is the enterprise admin. The enterprise admin owns the VCF infrastructure and is responsible for coordinating with the physical network to ensure proper connectivity. They also create projects, which represent the first level of tenancy. They define external IP blocks that allow communication between the virtual and the physical networks. These external IP blocks are then distributed to the individual projects, and quotas can be applied as needed. Importantly, the enterprise admin maintains full control over all networking resources. Next, the project admin steps in to manage the resources delegated by the enterprise admin, but without direct access to the physical infrastructure. The project admin is responsible for creating and managing VPCs, which represent this second level of tenancy. They also allocate resources such as IP pools and apply quotas to individual VPCs. Finally, we have the VPC admin, who acts as the end user in this model. The VPC admin can independently create logical networks and easily attach workloads to these networks. A key benefit of this model is that the VPC admin can fully leverage networking services without requiring in-depth networking expertise. This is all possible because the enterprise and the project admins pre-configure the underlying networking and resource allocations, enabling true self-service. The VPC concept has long existed within NSX, but with VCF 9 it's now fully integrated and consumable across other components of the platform. VCF automation leverages VPC objects, and VPCs are now exposed as first-class objects directly within vCenter. By default, NSX creates a default project that is fully configurable by the vCenter admin, who in this case serves as the enterprise admin, project admin, and VPC admin all at once. Other non-default projects appear in vCenter as read-only and cannot be modified from here. vCenter also displays subnets directly in the user interface, allowing you to easily connect a VM to a subnet, similar to how you'd attach a VM to a DV port group. In fact, both options are available side by side in the interface. NSX edges are essential service applications within the NSX architecture. Their deployment requires careful alignment between DV port groups and VDS uplinks on ESX hosts, and NSX edge fast path interfaces. This is often a complex task for less experienced users. A new deployment workflow, now integrated into vCenter, simplifies this process by guiding users through the necessary inputs, automatically mapping vSphere and NSX objects. And as an additional benefit, it provides a real-time visual representation of the configuration, which you can see here. This significantly streamlines the deployment of edge VMs, reducing complexity for non-expert users. We've seen that the VPC model defines three distinct roles, each with very clear responsibilities. Now let's look at how these roles work together to establish connectivity. New to VCF 9 is the multi-tier gateway model, which enables enterprise, project, and VPC admins to make independent connectivity decisions. The enterprise admin manages interactions within the physical network and provides connectivity options to project admins by defining external connections. These external connections are profiles that describe how access to the physical network is delivered. An external connection can represent either a connection centralized through a T0 gateway on an edge node or distributed access via a VLAN. The project admin, who has no direct access to the physical infrastructure, manages a new type of gateway called the transit gateway. By attaching the transit gateway to an external connection exposed by the enterprise admin, the project admin defines how the project connects to the external network. The choice of external connection also determines whether the transit gateway will function in distributed or centralized mode. And for the VPC admin, well, within each VPC, a VPC gateway is deployed. A VPC gateway connects internal subnets within each VPC and provides external connectivity by routing through the transit gateway. When attached to a centralized external connection, the transit gateway is associated with a T0 gateway on an edge node, effectively acting as a VRF of the T0 for those who are familiar with NSX. This tight integration means that all north-south traffic through the transit gateway also flows through the T0 gateway and inherits its redundancy model, whether it's configured in active-active or active standby mode. This has direct implications on the services the Transit Gateway can deliver, noting that stateful services are not supported when operating in active-active mode. In a similar way, VPC gateways also require a centralized component on an edge node to run stateful services. However, VPC gateways can be assigned edge resources independently of those used by the Transit Gateway in a centralized external connection setup. So the VPC gateway services such as SNAT and DNAT, DHCP, QoS, gateway firewall, supervisor cluster integration, as well as VCF automation, all rely on edge nodes, which is the key point here. The alternative to a centralized transit gateway, which we just discussed, which uses an NSX edge, is a distributed transit gateway. VCF 9 introduces the capability to deploy VPCs in a more simplistic way without requiring the configuration of an NSX edge. By attaching a transit gateway to a distributed external connection, each ESX host can independently route VM traffic to external destinations. However, the simplicity of this model does come with some trade-offs. Only basic services like reflective one-to-one NAT and distributed DHCP are available. And also, the physical network must provide a shared layer 2 domain across all ESX hosts. Unlike traditional NSX overlay networking, this approach requires external VLANs to be extended to each host. Enhanced Data Path is a high-performance virtual switch with two modes of operation, standard and dedicated. By default, new VCF 9 deployments run EDP standard mode on the VDS, while upgrading to VCF 9 will not change the VDS mode. Like the legacy VDS, the EDP VDS is interrupt-driven and uses CPU cores on demand. However, with its DPDK-based operations and packet data structure, it offers higher performance across all workloads without tuning. EDP delivers a 50 to 70% increase in performance, improving both bandwidth for large flow workloads and packets per second for workloads exchanging a high rate of small packets. EDP drivers optimize PNIC performance. Even older PNICs with limited features will see an improvement compared to legacy standard VDS settings. The dedicated mode assigns specific CPU cores for packet processing, offering even better performance for specialized workloads. It requires tuning based on careful consideration of traffic type and average packet size, and is typically used in telco environments. The legacy standard non-EDP VDS mode remains an available option.